everyone. It's great to meet you all today. My name is Maria, and I'm here to help you make sense of all of the different ways Python shines today in the world of deep learning. But before we dive in, let me share just a quick fun fact about myself. Python was actually the first language that made me fall in love with coding. It was the first language I learned. I was self-taught, and it just completely changed my path. It inspired me to study computer science and eventually start a career in the development sector. So fast forward to today. I have over a decade of experience working in leading tech companies. And for the past 5 years, my focus has been entirely on AI and deep learning, and more specifically, deep learning runtime and deep learning communication at large scale. So currently, I lead the runtime team at Habana Labs, the company that created Gaudi accelerators for deep learning training and inference. And my team basically handles all the core runtime aspects of deep learning. It means things like synchronization, hardware resource management, graph execution, and many other fascinating challenges that happen behind the scenes of large-scale AI training. And actually, after all these years, and after coding in more than 10 languages, most of them quite low level, Python still remains my favorite. So let's begin. Let's see what's on the agenda today. We'll start with the core terms and principles that every deep learning framework is built on. And of course, before we will break and compare frameworks, we must mention what a framework actually is. Then we will break down graph mode and eager mode, the difference between static graphs and dynamic graphs. We'll talk about the fundamentals, and then we'll move to the evolution of frameworks. Next, we'll highlight the strengths of the popular frameworks, PyTorch, TensorFlow, and JAX. And we'll see who is optimized for research, who is optimized for production, and who sits in the middle. We'll also explore large-scale training, which is becoming the defining factor of modern AI. We will talk about why scale matters, what changes when you go from one accelerator to thousands, and how different frameworks handle distributed compute. After that, we'll talk about deployment and production, and we'll wrap it up with the ecosystem. I think that by the end of this session, you will have a clear practical map of the deep learning framework landscape in 2025, and when to choose which framework, depending on your goals. So let's start. What are frameworks and why do we need them? As I said before we deep dive into the Python deep learning framework Showdown, let's start with this question. Just imagine trying to train a neural network completely from scratch. You'd have to manually code every single matrix multiplication, calculate every gradient, update every weight, and somehow make it all run efficiently on a chip or even across multiple machines. This is not just tedious, it's basically impossible at scale. So deep learning frameworks exist to hide this complexity and make it possible for us to focus on the ideas and not the math. They handle the heavy lifting, such as automation differentiation, so we don't have to compute gradients by hand. They handle the hardware acceleration, running our code seamlessly on CPUs, GPUs, TPUs, and custom accelerators like Gaudi. Model management, saving, loading, training, and deploying models with a few lines of Python. In other words, frameworks turn deep learning from a research experiment to an engineering discipline. They let us go from theory to production, and they do that fast. So let's take a moment to look at this illustration. On the left, we can see how chaotic and complex things used to be. Every line of code had to handle the math, the gradients, and the details manually. On the right, we see a completely different story. Clean, simple, and elegant. This contrast beautifully captures the true power of deep learning frameworks. They transform something once messy and technical into something intuitive and creative. Now, since we all come from different backgrounds, and not everyone here works directly in the AI sector, I'd like to just have a moment to explain some crucial concepts that will make the rest of this talk much easier to follow. First concept would be our work mode. And in other words, it's graph mode versus eager mode. This is to do with what actually happens to our training operations during runtime. It might sound technical, but it actually is quite intuitive once you see the difference. In graph mode, you don't actually run your operations immediately. Instead, you first define a computational graph. This is like a flowchart, describing how data should move through your model. Then in a separate step, you execute that graph with the real data. This approach might sound a bit clunky, but it has a big advantage. Because the entire graph is known in advance, the framework can optimize it before execution. Things like merging operations, reordering for efficiency, and distributing work across hardware engines. That's why graph mode is highly performant and still preferred for large scale. The downside is that it's harder to debug, because when you write down your code, nothing actually runs until you execute the graph. So if you made a mistake, you often don't see it until much, much later. In eager mode, everything runs immediately, line by line, just like a normal Python code. It's much more intuitive. You can print tensors, you can inspect values, and debug easily. No separate graph compilation step. This makes this ideal for researchers and prototyping, where you can want a feedback and interactivity. The trade-off is that eager mode is way slower because the framework cannot optimize the entire computation graph ahead of time. So you can think of it like this. Graph mode is like compiling a recipe before cooking. Efficient and repeatable once you know exactly what you're doing. On the other hand, eager mode is like cooking step by step, tasting and adjusting as you go. Now let's discuss graphs specifically and understand the difference between dynamic and static graphs. Or in other words, whether the graph can change during runtime. Deep learning frameworks differ, not just in syntax or APIs, but in how they execute your model. And this choice fundamentally affects flexibility, debugging, and performance. A static graph means the entire computation graph is constructed once before execution. Because the graph is fixed, the compiler can aggressively optimize it. It can fuse operations, eliminate dead code, pre-allocate memory, and map the graph perfectly onto the hardware. This is why static graphs shine in production, where performance is crucial. On the other side, we have dynamic graphs, where the graph is created on the fly, every time you run forward. This provides amazing flexibility. The network can change shape during execution, use regular Python control flow, and be debugged line by line. Dynamic graphs are intuitive, fast to prototype, and perfect for research. The trade-off? They're harder to optimize ahead of time. You get flexibility, but you give up performance. So before we dive even deeper into the frameworks themselves, let us talk about why this showdown actually matters. First, Python dominance. Despite all the new tools and languages emerging, Python continues to lead deep learning. It remains the foundation for almost every major framework, even though the ecosystem has become fragmented over time. And yet Python keeps holding everything together, thanks to its simplicity, massive community, and seamless integration with AI libraries. Next, the balancing act. Companies today are constantly navigating a tricky trade-off, research versus production. On one hand, researchers need flexibility and fast iteration. On the other, production needs scalability, stability, and performance. Each framework takes a different stance on this balance, and understanding that helps teams choose the right tool for their workflow. And finally, clarity. With so many overlapping frameworks and buzzwords, it's easy to get lost. My goal today is to bring at least a little clarity to show you the real strengths and limitations of each framework and help you see not just which one is better, but which one fits your needs best. Now, let's take a look at how Python deep learning frameworks have evolved over time. So it all began with Theano, one of the earliest deep learning frameworks. Theano introduced the idea of defining computations as mathematical graphs. And that concept became the foundation for everything that followed. It paved the way for modern deep learning as we know it. Then came TensorFlow, which took deep learning from research labs to large-scale production. TensorFlow revolutionized the space by focusing on scalability, distributed training, and robust integration across hardware, from CPUs and GPUs to TPUs. It became the go-to choice for companies that needed reliability and performance. A few years later, PyTorch arrived and completely changed the landscape again. PyTorch was built with flexibility and simplicity in mind. It gave researchers a way to write models that felt like normal Python code. It quickly became the favorite in the research community because it was intuitive, dynamic, and easy. Next, we have JAX, which represents a more recent evolution. JAX combines functional programming with automatic differentiation and XLA compilation, allowing incredibly fast, optimized code execution. It's popular among advanced researchers and teams pushing the boundaries of model performance and scale. So let us focus on the stars of this evolution, as I mentioned. In Python, we have the three frameworks that shape the way we build and scale today: TensorFlow, PyTorch, and JAX. They all speak the same language, but each with its own unique accent. Let us start with TensorFlow and Keras, the framework duo that really defined deep learning at scale. TensorFlow was created by Google Brain, and it became the standard for building production-grade AI systems. It's powerful, scalable, and built to handle everything from research to deployment. On top of it sits Keras, which acts as the friendly face of TensorFlow, a high-level API that lets you build and train models with just a few lines of code. Together, they form a perfect balance. TensorFlow handles the heavy lifting, performance optimization, and distributed execution, while Keras makes the workflow fast, intuitive, and human-friendly. TensorFlow and Keras really shine when it comes to production and scalability. They're the go-to choice for companies that need to take the model all the way from research to real-world deployment. They're also fantastic for cross-platform machine learning. The same model can run on mobile device, in the browser, or massive cloud cluster. Another major strength is its stable and integrated pipelines. TensorFlow offers a complete ecosystem. TensorBoard for visualization, TensorFlow serving for deployment, and so on and so forth. So overall, TensorFlow and Keras are best for when you need reliability, performance, and long-term maintainability, when your goal isn't just to experiment, but to scale. Now let's talk about PyTorch, the framework that truly changed how people think about deep learning. Developed by Meta, PyTorch introduced a completely new level of flexibility and interactivity. Its biggest innovation was the dynamic computation graph, meaning that operations run immediately, line by line, just like regular Python code. This made it intuitive, transparent, and easy to debug, which is why it quickly became the favorite. Basically, PyTorch was designed around immediate execution from day one, which made it the most intuitive framework for researchers. Even though it now supports compilation, its core philosophy is still eager first. So PyTorch is best for research, experimentation, and innovation. It's the framework of choice in academia and cutting-edge AI labs because it allows researchers to iterate quickly and try new ideas without friction. It's also great for rapid prototyping, when you want to test a concept, tweak a model, or explore a new architecture. PyTorch gives you an instant feedback. And in the recent years, PyTorch has grown beyond research with tools like TorchScript. It now bridges the gap from research to production. In short, if you want to move fast, experiment freely, and stay close to the Python experience, PyTorch is probably your best friend. And finally, we have JAX, the framework that brings together mathematical elegance and raw performance. JAX was developed by Google Research, and it feels a lot like NumPy, but supercharged. It combines familiar Python syntax with automatic differentiation, and XLA compilation, which allows it to run incredibly fast on GPUs and TPUs. What makes JAX special is that it was built for performance and scalability from the ground up. It's not just about training neural networks. It's about building the kind of custom experimental high-performance models that push the boundaries of what's possible. So JAX really shines in the advanced research and high-performance computing. It's the tool of choice for teams working at the cutting edge, like DeepMind and Anthropic, where speed, parallelism, and precision matter most. It's also preferred for multi-device and multi-node training. JAX makes it surprisingly easy to scale. In short, JAX is for those who need maximum control and efficiency, and who aren't afraid to trade a bit of simplicity for raw computational power. If TensorFlow is the production power horse and PyTorch is the researcher's playground, then JAX is the performance lab. Now let's look at what the numbers tell us. As of 2025, about 85% of developers use Python frameworks for their deep learning projects. This is an incredible level of adoption, and it shows how Python truly became the universal language of AI. Even with new languages and tools appearing every year, Python continues to dominate because of its readability, vast ecosystem, and strong community. On the right, we can see another interesting trend. Over 60% of professionals prefer PyTorch for research. This shifts highlights how PyTorch has become the framework of choice for experimentation and innovation, especially in academia. So while Python continues to lead the field overall, it seems like PyTorch is leading the innovation curve, bringing the gap between the research and production faster than ever before. Now, let us dive into one of the most practical aspects of those frameworks, their ecosystem and tooling. Because in real-world deep learning, the framework itself is only part of the story. What really matters is the ecosystem that surrounds it. Now let's start with PyTorch. PyTorch has built a rich and vibrant ecosystem that's loved by developers. You've got tools like PyTorch Lightning for structured training, TorchX for deployment, and integrations with Hugging Face, which powers many of today's cutting-edge NLP models. This strong ecosystem gives PyTorch a real advantage in productivity and flexibility, especially for research and rapid experimentation. Moving to TensorFlow. This one's all about scale and reliability. Tensor's ecosystem is extremely comprehensive. TFX provides full production pipelines. TensorBoards let you visualize. And TF Serving handles deployment at scale. Together, these make TensorFlow a solid choice for enterprise-grade end-to-end machine learning solutions. And then for JAX, the new, more research-oriented framework from Google. JAX leans into functional programming, and its ecosystem is evolving fast. You'll often see libraries like Flex and Haiku for building neural networks and Optex for optimization. These libraries make JAX incredibly powerful for high-performance research and experimental models, especially when running on GPUs. Finally, a quick note on ecosystem maturity. This plays a huge role in framework adoption. More mature ecosystems, like TensorFlow's, offer stability and integration, while newer ones, like JAX, prioritize innovation and speed. So when teams choose a framework, they're not just picking a coding style. They're choosing an entire ecosystem that determines how easily they can train, deploy, and scale. Now, let's talk a moment about the importance of large scale. Over the last few years, we've learned something remarkable. When you increase model size, data quantity, and compute in the right proportion, performance improves in a highly predictable way. These are the famous scaling laws, and they hold across language, vision, and multimodal tasks. Large models simply learn richer and more abstract representation. They reason better, generalize better, handle edge cases better. And it's not just quality. Scale accelerates iteration speed. If your team can train in days instead of months, you unlock an entirely different rate of innovation. You can run more experiments, test more hypotheses, and push research forward. Finally, there's a competitive reality. The frontier of AI is defined by organizations training at scale. Multi-billion parameter models on thousands of accelerators. If you're not scaling your training infrastructure, you fall behind not just in performance, but in the pace at which you can ship new capabilities. In short, scale is not luxury anymore. It's the foundation of modern AI progress. And for such scale, distributed learning has become essential. With that in mind, let's explore how the three major frameworks approach distributed training. Starting with PyTorch. PyTorch uses Torch Distributed and FSDP, fully shared data parallel, to enable multi-node and multi-GPU training with minimal overhead. It's designed for flexibility, supporting both data and model parallelism. PyTorch also integrates with DeepSpeed, which is essentially powerful for large models like LLMs, helping to reduce memory usage and improve scalability. Next, TensorFlow. TensorFlow's TF distribute strategy offers a variety of options for scaling across devices, from single machine setup to multiple GPUs to massive multi-node clusters. And when paired with Horvath, TensorFlow makes it much easier for teams to train large models efficiently while keeping their code portable across environments. Then there's JAX, which makes a more composable approach. It provides parameters like PMAP, Pidget, and XMAP that allows developers to distribute computation seamlessly across multiple devices. This approach gives researchers incredible control and performance tuning capability, ideal for high-performance workloads. Now that we've seen how models can train and scale, let's talk about the final step, deployment and production. This is where machine learning stops being a research and becomes real world. Let's start with PyTorch. PyTorch provides a dedicated deployment tool called TorchServe. It allows teams to serve PyTorch models at scale, whether on premises or on cloud, while maintaining flexibility and high performance. TorchServe supports features like multi-node serving, version management, and auto-scaling, which makes it a great fit for enterprise environments that need stability and control. Moving to TensorFlow, we have TF serving, which is one of the most mature deployment frameworks out there. It's built for speed, stability, and visioning. TensorFlow serving handles large production workloads efficiently, making it easy to roll out new model versions and A/B test models with minimal overhead. This is why many large companies still rely on TensorFlow in production. With JAX, things work a bit differently. Since JAX was designed primarily for research, it does not have a single official serving solution, but it offers great flexibility. Custom deployment setups can integrate with high-performance hardware like TPUs or accelerators. This makes JAX ideal for specialized environments, particularly in research labs or companies with custom infrastructure. Now, let's take a look at where these frameworks stand today and how their ecosystems are evolving. Starting with PyTorch. It continues to lead the deep learning community, especially in research and open source innovation. Backed by Meta and strongly supported by OpenAI, PyTorch benefits from a massive contributor base and a vibrant ecosystem of libraries, tutorials, and community projects. It's the framework that drives much of the cutting-edge work we see in Gen AI, reinforcement learning, and large language models. In short, PyTorch has a momentum in research and experimentation. Moving to TensorFlow, its strength lies in the enterprise and production world. TensorFlow remains deeply integrated with Google Cloud, offering everything from training infrastructure to deployment services. Many large organizations stick with TensorFlow because of its mature tooling and production-grade reliability. In other words, TensorFlow continues to dominate wherever stability, scalability, and support are the top priorities. And then we have JAX, which has become the rising star of the research and high-performance computing space. It's being rapidly adopted by institutions like DeepMind and Google Research for their most advanced AI models. JAX's combination of flexibility, composability, and raw computational power makes it the go-to tool for those pushing for boundaries of model architecture and efficiency. So the landscape of Python deep learning framework is evolving rapidly. As we look towards the future, it's essential to understand the unique strengths of each framework. PyTorch is ideal for researchers aiming for rapid experimentation, while TensorFlow is preferred for production-level solutions. JAX offers cutting-edge capabilities for high-performance training, particularly in research settings. In 2025, the emphasis is on hybrid stacks and cloud-native MLs, requiring developers to choose frameworks based on specific use cases rather than adhering to a one-size-fits-all solution. With accelerator awareness becoming critical, understanding how each framework interacts with diverse hardware will influence performance outcomes. Ultimately, the right choice hinges on your unique needs and goals, making it imperative to stay informed on these framework developments. Thank you everyone for joining me, and I really hope that I could bring some clarity to this topic.